about limits and continuity today. We are going to start with limits. We're going to review limits as you did in Calc 1, and then we're going to talk about what limits look like in Calc 3 now. Limits you did last year were in 2-space. So in 2-space, here's what you were looking at. You had some curve, and then you had some point. Let's call that x naught, y naught. And if you were calculating the limit as x approached x naught, you looked at that limit from the right side. You looked at that limit from the left side. And if those were equal, we said that the limit existed. Occasionally, you might have a hole, in which case the limit still exists as long as both sides of the function approach the same value. When would be some examples of a limit not existing? Right, like a piecewise function where the two pieces equal different values. One other time? A cusp, yeah. An asymptote. Here's what we're going to be looking at now. Limits in 3-space. Say we have some plane. Let's call it f of xy. And we have some point on that plane. And that point, let's say, is x naught, y naught. So in this case, what we're doing is we're looking at the limit as xy approaches x naught, y naught. So this time there's two variables that we have to consider. First question you need to ask yourself is there a point there? So by there, I mean x naught, y naught. So is there a point there? Or are we approaching a point? In 2-space, we looked at two paths, the path from the right and the path from the left. How many different paths are there approaching this single point? Infinitely many. Yeah, that's really important. There are infinitely many curves. That approach x naught, y naught, and z naught. So realistically, we are not going to consider every curve. So we have to figure out a better way to look at limits. So here's the first strategy for example 1. We are going to consider the function f of xy is equal to the quantity negative xy divided by the quantity x squared add y squared. We are going to find the limit as xy approaches to 1 of f of xy. When you guys first learn limits and we're calculating them, what was the first step that you would try? Plug it in. Okay, so we're going to do that and see if that gives us anything helpful. So we get negative 2 times 1 all over 2 squared add 1 squared, which gives us negative 2/5. That then is our limit. So that is what you hope, is that you can just plug in the point and you get a value, in which case that's the limit. Of course, that's not the most interesting kind of problem, so we're going to look at one that's a little more interesting. Let's consider the function negative xy over x squared plus y squared. So same one. This time we are going to find the limit as xy approaches 0, 0 of f of xy. Is it going to work this time to just plug in the value? No. Okay. So do you remember in the very beginning, so 4 minutes ago, we talked about in Calc 1, you looked at the limit from the left and the limit from the right. What we're going to do now is we're going to look at this limit along different paths and see what happens. We're not going to look at all the paths, obviously, but we're going to choose a few of them. So first, we are going to look at the limit along the x-axis. Okay, here's how you approach that. Along the x-axis, y equals 0. Okay, so that limit that we were calculating, the limit as xy approaches 0, 0 of f of xy. If we look along the x-axis, we're going to replace all the y's with a 0. So instead, this becomes the limit as just x approaches 0. If I plug in a 0 for y, I get 0 over x squared. So this is just 0. Okay, this is the limit along a single path. That is not our answer. Let's next find the limit along the y-axis. We're going to approach this in a similar manner. Along the y-axis, x is 0. So that limit as xy approaches 0, 0 of f of xy. If we look along the y-axis, we're going to replace all the x's with a 0. So this is really the limit as y approaches 0. So we get 0 over y squared this time, which is the limit as y approaches 0 of 0, which is also 0. Do you guys see what I'm doing, what this process is? Yes? Okay, we're going to look at one more. We are going to look at the limit along the path y equals x. So if we look at the limit as xy approaches 0, 0 of f of xy, specifically along the path y equals x, I either need to replace all the x's with a y or all the y's with an x. I'm going to stick with everything in terms of x. So this is the same as the limit of as x approaches 0. If we're looking along this line, all the y's are going to be replaced by an x. So that's negative x times x over x squared plus x squared, which gives us the limit as x approaches 0 of negative x squared over 2x squared, which is the limit as x approaches 0 of negative 1/2, which is negative 1/2. Okay, what do we think about the limit then? If it's 0 along the x-axis, 0 along the y-axis, and negative 1/2 along y equals x. Thoughts? We don't have to be right. What do you think? Is the limit 0? Is the limit negative 1/2? Is the limit something else? Okay, so maybe it suggests that the limit doesn't exist because we're not approaching the same value along every single path. So here's what we should have learned from this. It's highly inefficient. It's also very impractical. That being said, you're going to do more of that. And maybe the limit does not exist. Okay, so before we actually answer that question, we have a definition to write down. Let f be a function of two variables. And assume that f is defined at all points on some open disk centered at x naught, y naught, except maybe at that point, x naught, y naught. Okay. Let's picture this and then write the rest of the definition. This is what I'm talking about. We have some function, like we had before. That disk is down here. So our function has to be defined on this entire disk except at the center, x naught, y naught. Maybe it is defined, maybe it's not. That's not an issue to us. Then the limit as xy approaches x naught, y naught of f of xy equals L if given epsilon greater than 0, we can find. Do these look familiar from last year? Yeah. Such that the absolute value of f of xy minus L is less than epsilon when the distance between xy and x naught, y naught satisfies the following inequality. This should look familiar to you because you've seen this before. You've seen something like it before, at least. Here's what you all saw in Calc 1. Calc 1, you had some function, and you looked at some point x naught, y naught. And this was your x naught. And what you did is you picked a small epsilon that created some interval. So this was x naught add epsilon. This was x naught subtract epsilon. So this created some interval for you. And you also chose some values here. If that was your y naught, this was like this. And that's how you looked at the limit was in that interval. Does this look vaguely familiar? Some of those symbols and inequalities and stuff. Here's the good news. I wanted to show that to you so that you saw it. We are never going to talk about it again. Sound good? So now you've really gone through Calc 3 because you've seen that. That's all I care about, though. I will honestly never ask you about it. No problem. Okay. Okay. What this leads us to, though, is an important theorem that has two parts. First part, if f of xy approaches L as f of xy approaches x naught, y naught, then f of xy approaches L as xy approaches x naught, y naught along any smooth curve. So as f of xy approaches some limit, as xy approaches x naught, y naught, then f of xy is going to approach that limit along any curve. Second part of the theorem. If the limit as xy approaches x naught, y naught of f of xy does not exist along some smooth curve, or if f of xy has different values along different curves, then the limit does not exist. So if you can choose one path where the limit doesn't exist, or if you can choose multiple paths that have different values, you have shown that the limit does not exist. So that example number 2, the limit did not exist. We found different paths with different values, therefore the limit does not exist. Ultimately, here are your 3 options. So to approach any limit problem, first option is that you actually plug in that x naught, y naught. Like we did in example 1, you plug in x naught, y naught, and then you get your limit. Second option is that the limit does not exist, in which case you need to show that either there's a path where the limit does not exist, or 2 paths with different values. And then there's one other trick that we're going to talk about, probably at the end of the notes, to approach the limit. For our purposes, I am not going to give you a limit that exists that you cannot plug the numbers into. Did you guys hear that? So if you can't plug the numbers in, the limit does not exist, and you have to prove that it does not exist. You are going to do 2 examples right now. Here's your first one. We are looking at the limit as xy approaches 1, 2 of the function 5x squared y over x squared plus y squared. And then you are also going to do one where the limit as xy approaches 0, 0 of the function in the numerator x squared minus y squared, and the denominator x squared plus y squared, that entire quantity squared. So I want you to take like 5 minutes right now and try both of these, please. So start by plugging in the values. If that doesn't work, you're going to have to look at multiple paths. Looks like some of you are starting to have answers. Can you turn to the person next to you and see where you both are?
before it's like this. It's like,
I've seen people do that.
I don't know. No one's ever talked about that before you.
mine are just very,
It's just score 4. Not score.
How did this go? What did we get for number 3? 2. You should have just been able to plug it in. And then 4, you should have gotten that the limit does not exist. Okay, here's my work. So plug in 1 and 2, you get 2. Example 4, first thing you should ask yourself is, can you factor it? You can't. So because you can't factor, you can't take out any discontinuities. That suggests that maybe the limit doesn't exist. I looked at the paths x equals 0 and y equals x and got 2 different values. You should have been able to see x equals 0 and y equals 0 are going to give you the same answer. So it's not very efficient to try both of those. The ones that are best to try are x and y equals 0, y equals x. Sometimes you're going to have to go to y equals x squared or y equals x cubed. But generally, you're not going to have to go outside of that. Okay, in your packet and on a test, you cannot just write the limit does not exist like I did. You actually have to write me a sentence. The limit does not exist because the limit is different along these 2 different paths as shown. How did that go? Okay? Okay, one thing I want us to write down real quick, and then we are done with limits, and we're going to go on to continuity. Here's the big lesson in all this. To prove that the limit does exist, you essentially have to be able to calculate it. So as I said, we're not going to be looking at limits that do exist that you can't just plug the numbers into. Sometimes there might be some factoring and some canceling that have to happen so that you can take out a discontinuity. But if you can't plug the numbers in, the limit doesn't exist, and you just have to find the different paths that prove it. Okay, I told you there's a trick to limits. We are going to look at that, but we're going to discuss continuity first, and then we'll look back at the trick that you're going to need to use sometimes. Continuity is going to be pretty similar to the continuity that you learned in Calc 1. A function, f of xy, is said to be continuous at x naught, y naught, if f of x naught, y naught is defined and the limit as xy approaches x naught, y naught of f of xy has to equal f of x naught, y naught. So that should be exactly what you guys saw in Calc 1, just with 2 variables instead of 1. 2 important pieces to know in terms of vocab. If we say that a function is continuous on D, so D being some open disk, that occurs if the function is continuous at every point in some open set. Open set or open disk. There are also functions that are continuous everywhere. By everywhere, we mean every point in the xy plane. We have an important theorem with 2 parts that's going to help us with our continuity. First part, consider some function f of xy that is the product of functions. So g of x times h of y. This f of xy is continuous at x naught, y naught, if g of x is continuous at x naught, and h of y is continuous at y naught. That is significantly easier. So if you have a function of two variables, if you can split it up into a product of functions of one variable and then another variable, if those two functions individually are continuous, then f of xy will be continuous. Next one that's involved in this theorem is compositions. So compositions are continuous. So in this case, a composition would look like f of xy is g of h of xy. If h of xy is continuous at x naught, y naught, and g of u is continuous at u equals h of x naught, y naught. Any questions about the definition or the theorem for continuity before we do an example? Okay. First example, consider f of xy is 3x squared y to the fifth. I want to know where this is continuous. This relates to the first part of the theorem. We have two separate functions. We have this function of x and we have this function of y. So if we consider g of x to be 3x squared and h of y to be y to the fifth, those are both continuous everywhere. So in this case, g is continuous for all values of x, h is continuous for all values of y. What that tells us is that f of xy is continuous everywhere as well. Now, if we consider for our second example, sine of 3x squared y to the fifth. This one is a composition. So that 3x squared y to the fifth, we call that h of xy. That is continuous everywhere because we just showed above that it was continuous everywhere. Then we have sine of u, if we call that u. This is continuous everywhere. Sine is continuous no matter what value you substitute in. That then tells us that f of xy is continuous everywhere. Okay. Questions on continuity before we do one last example that goes back to limits.
So we have to write out all these things if we were proving it.
Yes. No, we're good to return to limits? Okay. Can I flip the page because I need more space? No. Okay. Gretchen, tell me when you're ready. Okay, great. Last example. let's look at the limit as xy approaches 0, 0 of y natural log of x squared plus y squared. Okay, at this point, we can't plug in 0, 0. So that would indicate to us possibly the limit does not exist. There's nothing that we're going to be able to do, though, to get rid of that natural log. Natural log is always going to be there. It's always going to be 0. Never take the natural log of 0. The other thing that you can do is you can switch your limit to polar. So that's what we're going to do. This, then, becomes the limit as r approaches 0. Specifically, we're going to look at 0 from the right side. If r is 0, you can't plug in 0, so that's going to be an issue. Y then becomes r sine theta, and then we have the natural log of r squared. So let's see if this is helpful. What this gives us then is the limit as r approaches 0 from the right side. That 2 I'm going to bring out. That's a property of logs. So I get 2r sine of theta natural log of r. Okay, if I plug in 0, I get 0, 0, and I can't do anything with that. So what I'm going to do is I'm going to move this r to the denominator. So I get sine of theta natural log of r over 1/2 r. If I plug in 0 from the right side to sine theta natural log of r, Brian?
Is that like 1/2 r, or is it 1 over 2r?
Look at that. Okay, is that better? Okay, thank you. Okay, well, let's start with that one then. If I plug in 0 here, 0 from the right side, what is the limit in the denominator? Infinity. If I plug in 0, so ignoring the sign really, if I plug in 0 to natural log of r, 0 from the right side, what is that? What's that limit? Mm-hmm. So we can use L'Hopital's rule? You excited for that? Okay. So we get the limit as r approaches 0 from the right side. Sine theta is just a constant. So then we get 1 over r over negative 1 over 2r squared. So this becomes the limit as r approaches 0 from the right side. Sine of theta times 1 over r times negative 2r squared over 1. One of our r's cancels, so we get sine of theta times negative 2r. Now we can finally plug in 0, and we get 0. So this is a rare case where the limit does exist, even though you can't plug in 0, 0. Now, I believe in your homework when you have to do this, you are specifically told to convert to polar. Okay, so I don't expect you to know to convert to polar right off the bat, but I expect you to be able to do it when I tell you to. And this is very rare. If it's on your homework, I think it's one problem. It is in your packet, though. How do we feel about limits and continuity? Excellent. Wonderful.